All right, here we are. We're doing Psychology 1. We're looking at sensation, which is the first part of the chapter on sensation and perception. So we're going to start this week by exploring sensation. We are going to explore seeing, hearing, and pain. I would like you to please review taste, smell, and vestibular sense on your own from your textbook. Next week we will explore perception. I'm going to walk you through an example here. Now, unlike being in a vegetative state, when Jean-Dominique Bauby woke from his coma, he was once again vividly aware of the world around him. He was able to focus on his conscious awareness or attention and attention on the people and the equipment in the hospital room. He could feel pain in his body. He was able to hear some of what was going on around him. Seeing, hearing, and feeling are examples of what psychologists call sensation. In sensation, sense organs of the body, for example the eyes, convert environmental energy, such as light, that is bouncing off the objects into neural signals that the brain can then process. Sensation, in this case seeing, is the first step to getting information into our minds. After sensation, you must understand the meaning of what you are seeing. Perception occurs when we interpret the meaning, the information gathered through our senses. Now, although Bauby's stroke didn't damage part of his hearing, although in Bauby's case the stroke that he had did damage part of his hearing, in his book, in part, his continued ability to sense and perceive the world. And although he lays motionless in the bed, Bauby was just as aware of what he was going on and going on as you are aware right now as you're watching and perceiving the images on this video and the sound of the video. So it's really important that in this chapter we're going to explore how sensation and perception take place in our bodies and the role they play in our everyday lives and the relationship between the two. So we're going to start with a couple of definitions, and I'm going to define sensation and perception now, and I'll probably do it again in part 2. Sensation is the process through which the senses pick up visual, auditory, and other sensory stimuli and transmit them to the brain. Perception is the process by which sensory information is actively organized and interpreted by the brain. So for this part 1 video, we are focusing on sensation. As humans, we have great senses. However, in the animal and mammal kingdoms, our senses are not all that good. The visual light we see is only a small portion of all electromagnetic energy. Even still, our vision is pretty good. Researchers have completed many experiments in an effort to determine our sensory limits or ranges. So what's the dimmest light you can perceive or the lightest touch you can perceive? The absolute threshold measures have been established by sensory psychology. Just as a threshold of a doorway is dividing a point between the inside and the outside of a room, the absolute threshold of a sense marks the difference between not being able to perceive a stimuli and just barely being able to perceive it. The absolute threshold is the minimum amount of sensory stimulation that can be detected 50% of the time. The difference threshold is the smallest increase or decrease required to produce a just noticeable difference, or JND. In sensation, that is noticeable 50% of the time. So if you're listening to music and start increasing the volume very slowly and stop when you notice the volume changes 50% of the time, that's the JND, just noticeable difference. There's another theory that looks beyond the physical stimuli of a signal and the JND. Signal detection theory takes into account the personal variations to stimulus detection. Things like the difference of what happens over the course of your own life. As you get older, not all your senses work quite as well as they did when you were younger. Or sensory capabilities. If you've got poor eyes, myopia or astigmatism, you need glasses to correct. Your motivation and previous experience can all affect what and how much we sense. According to the signal detection theory, the detection of sensory stimulation involves first the discrimination of a stimulus from the background noise. Now, what that means, the discrimination isn't the way you might normally use the word. If you're given a multiple choice question test and you have 4 answers and you correctly answer C, then you've discriminated against the other 4 answers, or the other 3 answers, and sort of selected the stimuli that you felt was best representative. So you discriminated the stimuli, answer C, from the background, the other answers. Or if you're in a room and you're listening to a teacher, I'll get to that. So first, separate the stimulus and the background noise, and secondly, decide whether the stimulus is actually present. So here's my example. When you're in a class, the professor is sharing information while at the same time there's a student sitting next to you who's listening to a YouTube video. The door is open and the heated argument that is occurring in the hallway can be heard, and the classroom is particularly cold. You're discriminating and honing in on what your professor is saying while ignoring all other stimuli is what signal detection theory is suggesting that we do. I remember being in class and saying, "You're discriminating my voice from all the other noise that's in the room here. Can you hear the sound of the fan that the projector is making?" And it was only at the time that I pointed it out that people say yes, they could hear it, but they weren't listening to it, they didn't hear it, they discriminated and separated that as background noise and didn't hear it from the sound of my voice in the classroom. So for each of our senses, there is a specific sensory receptor for whichever type, which detects and responds to the sensory stimuli. They detect and respond to one type of sensory stimuli and convert that stimuli into neural impulses. Transduction, it's the process by which sensory receptors convert the sensory stimuli into electrochemical neural impulses that are sent to their own specific locations in the brain. I mean, holy crap, eh? That's very complex and happening so rapidly, so many times a day. You just think about that. We'll come back to it. Now, this is called what is called sensory adaptation is the process in which sensory receptors grow accustomed to the constant, unchanging levels of stimuli over time. Now, my wearing shorts in the winter is an example. I've gotten used to the cold where my body doesn't react to it in the way that the cold might react to you. Smokers can grow accustomed to the smell of cigarettes. Daycare environments, they can get used to the noise and maybe the aromas of a daycare environment over time. And these would all be examples. I worked on a farm for a while, and smelling like manure was something I went, oh God, people are going to notice. But living in a farm community, everybody has a bit of that in the course of their day, and it's not something, it's sensory adaptation. Okay, let's carry on with, we're going to look at light, hearing, and pain. And we'll start with light, light and what we see. Now what I'm going to do is I'm going to walk through the process and highlight a few points, but you'll find more information, of course, in your textbook to help you understand. Now, our eyes, for the most of us, the sensory experience we rely on the most. Let's look at the parts of the eye that enable us to see. Essentially, we're going to start with light bends. Light is bent in the cornea, and it's bent inward through the pupil, the small dark opening of the eye, and the iris will dilate and contract the pupil to regulate the amount of light that enters the eye. The lens changes the shape, and it's known that process of changing the shape is accommodation, as it focuses the image of the objects from varying distances onto the retina. A thin membrane containing sensory receptors for vision is in and around the retina. In some people, the distance between the lens and the retina is too short, and that's known as myopia. or it's too long, or hyperopia. But this can be corrected through glasses or contact lenses, or in more modern times, of course, through LASIK surgery. Now, at the back of the retina are the light-sensitive receptors known as rods and cones. Rods detect changes in brightness but don't see color, and they function best in low light. They do not respond to different colors and are found everywhere in the retina except the center of the fova. Now, this might explain why when you're out at night or in a dark room, you can see a little bit better when you look to your peripheral. Because as the light enters your eye, whatever light's available in a dark area, and it's surprising how much light is actually available outside, stars, moon help that, night lights in your room, reflected lights from different places can help. But whatever light does get into your eye on that angle, it angles the light towards the side of the eyes. And that's where the rods are, and that's why you're able to see a little bit better in the dark room if you don't look directly at things, but you look off to the corner of your eye. Being that's where the rods are, that's why you can see a little better in the dark off to the side. Now the cones, these are sensitive to colors and work best in bright light. And they're responsible for the sharpness and visual information that are found in the fova. So when light enters the eye, it needs to pass through 4 layers of cells before hitting rods and cones. The ganglion cells, the amacrine cells, bipolar cells, and horizontal cells. Now once lights get through to the rods and the cones, the sensory receptors, transduction occurs. Now the rods and the cones turn light into neural impulses. That's transduction. These neural impulses next flow through the optic nerve, and that's the pathway that the neural impulses will travel from the eye into the brain. But what's interesting is that these optic nerves from your left and your right eye, as they get deeper towards your brain, cross over at what's known as the optic chasm. And so this is where they cross over. Your left eye goes to your right, and your right eye goes to your left side of the brain. Now the impulses continue through the optic nerve to the thalamus. This is where the impulses are transmitted to where they are analyzed by our visual cortex. The visual cortex then distributes the details to the appropriate locations where they get, and we start to have meaning. So because all this information comes in so many different it comes in as a neural impulse, it has to get to the visual cortex towards the back here, that then can figure out what that all means and send it into its parts, send it to the parts of the brain, which will then help us make sense. I just find this to be absolutely amazing, the way that our sensation works. In color, what makes things more meaningful and rich are 3 things: that hue, saturation, and brightness are the dimensions found to influence the more subtle and significance of our color distinction. So we're going to look at the theories of color vision. And there's 2 we're going to predominantly look at. Trichromatic theory and the opponent process theory. The trichromatic theory states that there are 3 types of cones in the retina. Each make a maximal chemical response to one of 3 colors: blue, green, or red. Each cone is sensitive to one of those colors. All colors would be perceived as a combination of these 3. And the retina does indeed have 3 kinds of cones. Very good. The second theory is the opponent process theory. Now, opponent process theory of color perception presumes 4 primary colors of red, green, and blue, and yellow. Cones are arranged in pairs, and when one member of the pair is activated, let's say green, then the other is not. And in fact, you can tire it out. Here's a demonstration I'm going to put up on the screen here. I want you to, and you can do this in your textbook, but I'll demonstrate it here. You see behind, I want you to stare at the dot in the middle there of the green and black flag for approximately 1 minute. I would recommend to give this a try just so you can see how this works. Pause the video for a minute, stare at that green black flag at that dot, and then start the video and shift your gaze to the dot on the blank white rectangle and tell me what you see. So take a moment. I'll wait. Now I know that's not been a minute, but I'm going to go ahead. I know you could pause, but I want to make sure I get this done in a reasonable time frame. What you just experienced is what's called the negative after image. Now, what I'm going to do here is just walk you through both theories quickly in terms of both theories have merit because each explains a different phase of color processing. Researchers believe that color processing starts at the level of the retina, continues through the bipolar and ganglion cells, and is completed in the color detectors in the visual cortex. The trichromatic theory is consistent with that, with what happens within the cones, and the opponent process theory is consistent with what happens in the ganglion cells. And so what you can see when you do that flag experience, you've tired out, if you will, you've over-exhausted the green of the green-red cone, and so when you have a white background, the green is tired, it can't produce, but the red portion can, and that's why the flag turns into what we would normally see as a Canadian flag. All right, let's move on to sound and what we hear. In order to be heard, sound requires a medium through which to move, air, water, or some other solid object to carry sound waves. Sound has characteristics that make up the detail, and we're going to review them. First we'll look at is frequency, which is the number of cycles completed by a sound wave in 1 second. So a sound wave looks not unlike a water wave. It's got a high and a low, and it moves. And so the speed in which the two high points travel in a second is what is frequency. And this determines the pitch of the sound. Frequency units are measured in hertz. Then there's amplitude, which is the loudness of the sound. The unit measured here is a decibel. And so when you hear about something being at 50 decibels as opposed to 100 decibels, that's the loudness that's being measured. And decibels are units of measured for loudness. Timbre. Now this one's a little bit, it's hard to explain, but it's easy to hear. Timbre is the distinctive quality of a sound. It distinguishes it from other sounds of the same pitch and loudness. For example, a trumpet and a violin are different when each plays a B note. They're both playing a B note, they can both play music of the same song, but you would clearly distinguish the two as being different instruments and making different sounds. The quality of that sound is different, and that's timbre. Now, hearing involves sound waves entering the pinna, the visible part of the outer ear, and travels to the end of the auditory canal, causing the eardrum to vibrate. In the middle ear, which amplifies the sound wave, the vibration of the oval window causes activity in the inner ear, setting in motion the fluid in the cochlea and moving the hair cells and receptors, which can transduce, there's that transduction again, transduce the vibrations into a neural impulse, the same as with sight. The auditory nerve carries the neural impulses to the brain. It sounds very similar to vision, and it is, just a different sensory apparatus, if you will, but they're both using sound and light waves and translating that into electromagnetic neural impulses. Now, there's two major theories that attempt to explain hearing. One is place theory and the other is frequency theory. Place theory, it states that the location of the hair cell on the basal membrane is important, and it corresponds with different pitches. As you can see in the image, there's a cochleal, so it looks like a shell. And where the hairs are on that shell where in place they are will be the different frequency, the different sounds that can be made, different pitches. This explains pitches above 1000 hertz, but it doesn't account for pitches that are below 150 hertz. Now, frequency theory, it states that the speed with which the basilar membrane vibrates corresponds to different pitches of sound. Now, this explains pitches below 100. So the frequency theory best explains how we perceive low frequencies, and the place theory explains how we perceive high frequencies better. And so there's an example where we have two theories, although different, combined, they help us understand how our hearing may work. Now we'll touch on pain and touch. Nerve endings in the skin, the sensory receptors, respond to different kinds of stimulation, including heat and cold, pressure, pain, and a vast range of touch sensations. Neural impulses ultimately register in the somatosensory cortex part of the brain. So in all instances for our sensations, there being different stimuli, sound waves, light waves, touch, are transmitted in a way that neural impulses are produced and taken to the brain. When we look at how we experience pain, we'll use the theory of gate control theory. Holds that pain signals are transmitted by slow conducting fibers and can be blocked at the spinal gate. First, if fast conducting fibers get their message to the gate first, or secondly, if the brain itself inhibits their transmission, gate control theory of pain states that when receptors of sensitive pain are stimulated, a neurotransmitter is released to the spinal cord, activating other pain receptors by opening gates in the spinal column and sending the message to the brain. So when we apply ice, heat, electrical stimulation, or rubbing a knee area, we can block pain sensations. So if you can remember ever having a sore or a scrape and you ran home crying to your mom or your dad and they kissed the boo-boo, make it better, this actually might help. It's the same as rubbing an area, if you will, and having that be the superseded message that gets through to the brain that the pain may not be as strong of a sensation at that time. Endorphins, released when we are stressed or injured, is the body's natural painkillers. They block pain and produce a feeling of well-being. Now, this has been a relatively quick portion, so please make sure that you spend some time going through your textbook, making notes, highlighting things so you can prepare for the first test, okay? This is the end of part 1, sensation. Please remember to review smell, taste, and vestibular senses on your own. Next week is part 2 on perception and how we use our senses to contribute to how and what we perceive. All right? Thank you, everybody, and we'll see you next week. Keep up the good work. Bye now.